related to functional safety. So how must embeds functional safety guided by the requirements of the ISO 26262? So without, then we'll have, of course, at the end of the presentation, Q&A sessions as before. So I do invite you to post your questions in the Q&A chat. Okay, so without further ado, I will pass the presentation, the floor to Licinia. Please, Licinia.
So yes, I'm going to talk about how the new developments in MIPI are guided by the requirements of ISO 26262, the reference in automotive. So I'm going to start by just giving a quick intro on what's going on in automotive, a very brief update here. Obviously, there's a lot of things happening in automotive, and starting with the architectures, a lot of discussions about the transition from more distributed architectures to more centralized, or a combination of distributed and centralized. In a way, more functions potentially being consolidated in a single SoC. So that's definitely one aspect. The other aspect is the growing number of sensors and different types of sensors producing a lot of data. We're talking about image sensors, LiDAR, radar, infrared. So all this data coming into these domains, which will improve the opportunities for sensor fusion and enable more applications in the context of ADAS, infotainment, and connectivity. We're talking about complex systems that need to make decisions very quickly, that need to process a lot of data. So another thing that we're seeing is that we see, everybody observes, is that these chips are being implemented in, they need to be high performance, and are being implemented in advanced FinFET nodes. So high complexity SoCs that we're talking about. And then finally, we're talking about automotive. These chips need to, these solutions, these systems, they need to address the stringent operating requirements of automotive, and that's why they need to be designed to meet the functional safety, reliability, and quality requirements that are common in automotive. So in a high level, that's kind of a description of the trends. The MIPI in automotive, right? MIPI is a lot of the specs for MIPI are being adopted in automotive. MIPI was born in mobile, but evolving into a more mobile vision imaging platform, and obviously being adopted in automotive. Why? Because these specs, these interfaces, specifically image sensors connecting with displays, storage. So these interfaces are adopted, are already being shipped in billions of units in other applications such as mobile. So as Peter mentioned, these are very well proven. They enable a low cost implementation, and so that's why they're being adopted in automotive. So this is a list of all the different specs that are being used in the context of, are available and being used in the context of automotive, and most recently with the introduction of API. Also, MIPI can handle the long reach connectivity, intra-box connectivity in the context of automotive. So this slide here represents the very simple representation of the connectivity, the MIPI in automotive in terms of connectivity. On one end, we have the sensors, the image sensors, the LiDAR, radar, that need to connect with the ECU. And then from the ECU, from the processing unit, also driving data to the display, right? So how do you do that? The diagram on the top kind of gives you an idea of how the short range solutions, C-PHY, D-PHY, connect with a long range solution, right? From the sensor to the bridge to the ECU, and then from the ECU to the display. The long range solution, so there's some options, some solutions being adopted, but API comes in with its own merits as an alternative, as a very interesting solution to address this requirement for long range connectivity. So this is, again, the diagram on the top is more a bridge approach, which is probably more common today and probably a few more implementations will follow the same approach. Into the future, as mentioned already here in different sessions, there is an opportunity to bring this native support for API at the sensor, at the display, and basically simplify the connectivity. That's from a connectivity point of view. In terms of protocol, the different specs for CSI for camera, BSI for display, introducing more and more capabilities to address the functional safety requirements, the security requirements, and the content protection as well, which is particularly relevant in display use cases. So now, how are these protocols evolving to address the automotive requirements in terms of functional safety? So it's important to look at the reference, ISO 262-625 Annex D, that describes the ingredients, what kind of safety mechanisms these communication buses need to have in order to address the automotive requirements, the functional safety requirements in automotive. And here highlighted, so there's a list of items that are relevant, and highlighted, you can see the items that were definitely picked up by MIPI in order to bring more developments into the different protocols. And so here, I'm going to touch about camera and display in particular. So this is the starting point, the base, the reference that guided the new developments. And so the developments from MIPI for both camera and display, they come as in the form of service extensions, CSC, camera service extension for camera, obviously, DSC, display service extension for display, right? And it's all about having end-to-end functional safety and security for these kind of for these applications. And we're talking about different levels of protection: packet-based level, frame-based, even the region of interest, the regions of interest in the case of the imaging, and also whether you're using compression, if the compression is being enabled or not. So all these levels of protection, basically bringing that end-to-end protection for safety and security. And so the bullet below, it's kind of listing how these ingredients that came in from ISO 26262 are embedded in the spec. So basically, we're looking at CRC with handling distance bigger than 3. This is in order to detect any communication failures and bad payloads. The message sequence counter to be able to detect packet loss and duplication, to be able to report that to the system so that the system can take action, right? This type of situation if you look at a consumer application, you may be okay if you drop a few packets here and there, but in the context of automotive, that can have consequences, dramatic consequences. So making sure that all that information is reported to the system so that the system can take action. Having the task pattern generators for testability, and fault injection provisions to be able to check if whatever mechanism is in place is working properly. So whether it's on the camera side, CSC or DSC, these are the main elements coming from ISO 26262 that are now embedded into the new MIPI specs. And this is how the stack looks for CSI-2 kind of application with CSC, with those extensions. Nothing really changes, right? So if you look on the right side, it's the CSI stack on top of C5D5 implementation, which is very common today. And the service extensions are embedded at the protocol level there. And on the left side with A5, so the stack where you have the same service extensions embedded in the protocol, and then obviously there is the necessary adaptation layer for A5, but that's A5 specific. So from a functional safety point of view, the service extensions are embedded in the main protocol there. So now we talked about how the spec is evolving, and it's interesting to look at what this means when you're designing for automotive, right? When you're designing for automotive is different from designing for consumer applications. The fundamental difference is the stringent operating conditions. And so there are three fundamental pillars that need to be addressed when you're designing for automotive. The functional safety, which we touched a little bit coming from the MIPI spec. You also need to address the reliability requirements, make sure that the systems are qualified for automotive, can handle the operating conditions. And then obviously everything needs to be done with a very rigorous quality management system. And here I want to go through this. I want to touch on these items briefly. Again, we already talked a little bit about functional safety, and I want to expand on that. And basically, my point here is when you're designing for automotive, when you're designing for functional safety, there is ISO 26262 also defines a flow for that, right? So in this diagram, it's the typical V-shaped model for development. In purple, you see the consumer flow, from architecture on the left side to implementation, and then on the right side, the verification. And the point here is that when you're designing for ISO 262 functional safety, there are a number of activities and work products that need to be added in different stages of the design flow. And so on the left side, if you look at the level at the time of architecture and core specification, this is where you start looking at your safety plan, defining the safety requirements, defining the safety goals, and then start implementing safety features. And here I want to pause a little bit, and this is where I think it's particularly interesting, the developments from the MIPI spec, right? So at this point, when you're defining what safety features you need to include in order to meet your target safety levels, you were looking at the protocol. And obviously, if the protocol has native provisions to address the safety goals and the safety requirements, then everything is easier. But at this point, at the implementation level, this is where you also define those new safety features that need to be included. So once you have the safety features, you move to the verification, you go through the fault injection, which is a requirement, look at the coverage analysis, and then you have your FMEDA report where you basically confirm if everything that you did so far will allow you to meet the target safety level, whether it's ASIL B, ASIL D, ASIL C, etc. Finally, the safety manual, it's where all these safety features are documented in terms of how they should be used, what kind of information they produce. And these safety features can be internal to the IP or to the SoC, but they can also be external safety mechanisms that are expected to be present in order to enable the target safety level. So that's a perspective about the flow. I talked about in the previous slide, so I talked about these safety features, right, that you need to implement in order to target these safety levels. And in this slide, I'm kind of giving you a generic overview of the types of safety features that are needed in order to target those safety levels. And we're talking about things in terms of protecting interfaces, protecting the whatever buffers they're using to implement the protocol, redundancy, make sure that you protect critical circuits, and other aspects related to the functionality that you're implementing. So it's in general, you need those safety features in place in order to achieve those target safety levels, which is represented here on the right side. It all depends on what are the requirements of the application, if it's for a drive assist or for self-driving. And here's an example of a best-in-class implementation of a CSI-2 interface, where the boxes around the purple boxes, they describe different safety mechanisms that were implemented in order to achieve an ASIL B safety level, right? And you see things related to parity protection at the interfaces, data path protection, ECC for the buffers that you need to implement the protocol, the register space protection, etc. Now, a new version of this implementation with a new version of the MIPI spec with already guided by ISO 26262 means that probably not all of these capabilities need to be in place in order to achieve the safety levels, but some of them will still be required. For example, the FIFOs that you need to implement the protocol, you need to make sure that whatever FIFOs, whatever buffers you're using, they need to be protected. Those ECC for closely coupled SRAMs for the implementation. The register space protection, it's something that it has to do with the implementation, right? So you want to protect the register space for this interface. Make sure that the last thing you want is having one of the bits flipping and changing the operation of the interface completely. So from an implementation point of view, you need to protect the register space. And then there's things again related to the implementation, critical state machines, clock domain crossing, all these sensitive circuits. You want to make sure that those are protected, and that has to do with the implementation. Then, as a result, this building block will have additional safety mechanisms that have their own reaction time, they have their own flags, and need to be managed. And in the next slide, I want to kind of bring this into a vision of system level, of SoC level, I mean. And the idea here is that, my point here is that the building block, the MIPI CSI building block, which has those functional safety capabilities, the functional safety strategy needs to tie in with the system level view of functional safety as well. And so what I want to highlight here is that a very common industry technique is to have an entity, a safety manager processor at the system level that offloads everything that is related to functional safety, and basically is responsible for managing things like the system failures, the real-time faults, and safe boot and mission mode testing. So all these aspects related to functional safety are managed by this entity and offloads the other processors because they're doing other important things related to the application itself. And this is, so far I've talked about functional safety. Another aspect that I mentioned when I mentioned those three pillars, it's reliability. And we all know that these parts, all these systems, they need to handle stringent operating conditions, environmental, temperature, noise, vibration. They need to be active. The long-term operations is important. Compared with consumers, you can see in the diagram, automotive designs are expected to be out 15 years or even more, and they cannot fail, right? So reliability is key, and we all heard about ACQ 100 qualification, how these systems need to pass qualification that is defined by ACQ 100 in order to go to automotive. The point that I want to highlight here is that when you're designing for automotive and you need to make sure that the part is qualified, you need to design in we need to design in reliability. And so at the design stage, you understand what type of temperature profile the system will be exposed to. It all depends if it's in cabin, under the hood, though the mission profile here will vary. And that will influence the design rules, the tech files, all the inputs at the design stage. And so that will guarantee that your design will, once it is implemented, it will be qualified, will be able to pass ACQ 100 qualification tests, and ultimately will be qualified for automotive. That's kind of the point here. And so we talked about safety, how the MIPI spec is evolving, and how you need to design for functional safety as per ISO 26262, all the additional activities and work products that are needed. We talked about reliability and the importance to design in reliability to make sure that your design will be qualified for automotive. We didn't talk much about quality, but the quality, again, very important in automotive. Everything, the development flow needs to be tracked, and effectively, you need a very robust quality management system so that you can manage the flow, and you can also provide evidence of what you did for automotive. So also very important. And so these are the three items. And the point that I want to highlight here is designing, when you're designing your next generation automotive SoC in the main automotive nodes, 16, 7, 5 nanometer, obviously you need to look at the building blocks, the interfaces that are needed for camera, for sensor connectivity, or for display. You need to make sure that those are available in the right process node and comply and support the required specs in terms of CSI, DSI, and physical layers. But you also need to look at it from a holistic perspective, that that package also needs to include ingredients that will support the development flow, all the activities for automotive related to safety, reliability, and quality. So that's an important message that I want to highlight here. And with that, this is what I had to say right today. Thank you very much for your time, and I think we have some questions here, Michelle.
Okay, thank you, Lucian. That was a great it was a great presentation. I think it was really interesting. Yes, so we have a few questions. Not much time because I think we have to give time for the next presentation. In your opinion, how are the automotive functional safety requirements likely to evolve in the next future, based on your knowledge?
Yes, sir. It's a interesting question. The one thing that I stressed a lot in this presentation was the target safety levels, and the target safety levels is tied to the autonomy levels as well, right? So if we look at the market today, the majority of the market today, for a given target autonomy level, there's a target safety level, and the FuSa requirements are aligned with that. So if you're designing for ASIL B, the FuSa requirements are aligned with ASIL B. How can this evolve? Obviously, as the industry moves to high autonomy levels, my expectation is obviously that the safety targets will increase, and as they increase, I can see that more requirements will come in terms of FuSa, right? More ingredients, more safety mechanisms will be needed in order to achieve those target safety levels to enable those higher autonomy levels. That's kind of my view on that.
Okay, good. Thank you. Thank you. So you mentioned that there are different configuration for the automotive network architecture, distributed, centralized, zonal, and so on. Does that type of architecture impact the automotive IP, the way you develop it?
If I understand, there's the architectures, the architectures in automotive for automotive systems are evolving, right? So from more distributed to more centralized, or a combination of that, that needs to solidify. But the impact for IP, if we zoom in into one particular IP, I don't see a big impact. I think the impact is more the different type of IP that it's needed, right? Because you may need an interface that has better characteristics for point-to-point streaming capabilities, or you may need, if you need to connect domains, you need some chip-to-chip kind of connectivity that requires different characteristics in terms of managing the chip-to-chip connectivity. So the impact from an automotive IP point of view is, in very simple terms, I would say that more different types of interfaces would be needed. More streaming, for example, there's big names out there in the industry already being used, but the impact would be there will not be a single IP solution that can cover all the connectivity needs. There will be probably a few that will be used for different use cases.
Okay.
That's an attempt to answer to that question.
We have one more question. How does the use of a full stack industry standards such as MAS help IP vendors?
The IP vendor. So from an IP vendor point of view, we want to provide a proven solution, right? And the idea of having a stack that leverages the same physical layer, right? Different protocols on top of a physical layer, it helps in delivering a high quality interoperable solution, making sure that the protocol stack works with the PHY, because we don't have different types of PHYs. We have one PHY that can support camera or display. So from an IP point of view, we can focus our energy in designing high quality interoperable solution meaning protocol plus PHY that can be used. If things were more fragmented, more PHYs, one PHY for camera, one PHY for display, that would create additional challenges for the IP provider to maintain those two developments. So a single stack with a common PHY physical layer, with a common physical layer, it is an opportunity to deliver a better solution to the industry.
Okay, thank you. I think we have time for a couple of more questions. So next question is, will end-to-end protection make the hardware cable diagnostic features unnecessary?
Can you repeat the question, please?
Yeah, basically, will end-to-end protection, you mentioned in the set points, you have an end-to-end protection. Would that make the hardware cable diagnostics features unnecessary, no longer necessary?
I cannot elaborate much on that. I cannot take the risk of saying that it will not be needed. I think everybody, functional safety is a complex topic, and safety mechanisms coming from different directions are all contributing to the same goal of a robust link. So I would describe it just different levels of safety mechanisms to address different aspects of the pipeline. So not discarding anything at this point.
Yeah, I think I kind of see that, because in an end-to-end, you have different steps there. You've shown before some slides, where it goes through different stages and layers, some physical, some in the chip. So end-to-end, it would only tell you that things are not being compromised, but it does not tell you which part of the system is being compromised. So we still need some feature there. Okay, but I think time for one more question is, during the you showed the slide on the ISO 26262, and there were some topics which were identified by MIPI as relevant. Which was the sort of the philosophy behind that? Because, for example, I noticed that transmission redundancy was not included. It just to see how was decided what to keep and what to leave out, and what to focus on and what.
I don't have an answer to that.
Okay, okay. I guess that was the a working group decision. Just. Another question for me. I'm curious because on the last slide you showed that the technology is evolving. You're going you showed from 22 nanometer down to 5 nanometer. Mm-hmm. How does that impact, or it does impact in any way, the functional safety work there?
Okay, interesting. As you go from 16 nanometer to 5 nanometer, if we look at the mass stack, there is the physical layer and there's the protocol layer. The protocol layer is essentially technology agnostic. So no impact there, because it's more modeling functionality from IP vendor language is RTL, it's soft IP. So we can basically bring it down to 16, 7, and 5 nanometer. So no impact functional safety at the protocol level. If we look at the physical layer, there might be some need to review the functional safety aspects as you move to 5 to below in terms of nodes, because then we get into the technology aspects, how it can affect the functionality of the physical layer. So you may need to revisit the functional safety strategy as you go to advanced nodes, because of the physics associated with advanced nodes. On the reliability, so that's functional safety. On the reliability, for sure you need to review the reliability strategy, which kind of ties into functional safety in terms of mission mode operation. And so that's why that's where the Foundry comes in, providing the necessary tech files so that you can update the file implementation in advanced nodes. So that's where there is definitely more impact.
All right, thank you.